Yeah, let's look at this. They say on proof by a counterexample, they say that it is common to prove a false statement by using counterexample. So what we should know here is that this is for disproving. If you want to disprove, or if you want to prove that something is false, you use counterexample. For an example, they gave us this here. They say that prove using counterexample that the following statement is not true. You see, right? So it is for us to prove that a certain statement is not true. And they give us a statement. They say that for a, b being integers, if a divides b and b divides a, then a is equal to b. You see, right? So we can come and let two different numbers, a and b, which are different. And then, or we can do this, we can say let a b be an element of an integer such that a is also 1 and b is also minus 1. These are integers. Now they say that a divides b. When we say a divides b, we are saying that a over b. All right, when we say a divides b, we're saying that a over b will not leave any remainder. That's what we are saying. A over b will not leave any remainder when we say that a divides b. Now, if I put my a as 1, then I put my b as -1, this does not leave a remainder. And when you say b divides a, we are saying that b over, let me say this manish when I'm reading this statement in other way. Okay, let's read it like this. We say a divides. I thought that's I was seeing a divides and all that. If we say this divides b, in other words, a should be in the denominator. When we say that b divides a, we are saying that b will be in the denominator. It is the one that divides. So, which this is fine. So we're going to have, this is correct, b over a, which is -1 over 1, which is equal to -1. They all divide, but then a is not equal to b. Remember here the statement says that if a divides b and b divides a, then a is equal to b. But here we can say that a is not equal to b. You see, right? So this is how we disprove. This is how we disprove something. So we'll look at some questions here. We'll try to use counterexample to disprove, right? We'll look at some questions where we can look at counterexample and check how do we disprove a statement. So let me see if we can look at some examples or on the tutorial. Let's see if on the tutorial we have something that says we should use counterexample. Let me see. Yeah, I think we don't have counterexample here, right? Yeah, there's no counterexample. I'll try to look for some questions of counterexample, and then we'll see how can we do them. All right. But if we check here, after writing this, a divides a, this one is b divides a, this one is a divides b. After writing them and letting a be equals 1 and b be equals to -1, we realize that indeed this thing does divide. Remember I said that when something divides, we are saying that it won't leave a remainder. Even if I would let a to be equals to 2, you're always going to let elements that will disagree at the end. And you let different numbers. So if I take a to be 2 and b to be -2, if we check, a over b will be 2 over -2, which is -1. Or this one can even be 3. It doesn't have to, they don't have to be the same, right? And this will be -3, -2 over -3. And then we'll have again b over a This is actually they leave a remainder. Like let's put the ones which do not leave a remainder. I think we have to put them like this. It's fine. They must not leave a remainder for them to devise. So we'll have 2 minus 2, and also for the other one, this one will give us -1, right? Also for the one which says b over a, we'll have -2 over 2, which will also give us -1. Even though these things are not giving us a remainder, they do devise, but then a and b are not equal. You see, right? So at the end you say a is not equal to b, hence our statement is false by counter example. You see, right? Then you write something like that. And then now let's go to contrapositive. We can come to contrapositive. Guys, contrapositive is simple. We can look at this one example, then we go to the tutorial to try and attempt at least 2 questions there. And then we do that individually, right? So now when we check here, we are told that they say to prove that the statement P implies Q by contrapositive. Sometimes this is called contraposition, right? Sometimes it's not called positive. We can call it this, right? Contraposition. So we assume negation of Q and deduce negation of P. In other words, if we are given P implies Q, if you're given this P implies Q, for contrapositive, you are going to write it like this. You take this one, you put it first, you negate it. You say implies, you take this one, you put it on the other side, you negate it. It's like I'm taking this to this side, it gets negated. I take this to this side, it gets negated. You see, right? Then I'll have negation of P. Now I'm going to prove this as if I'm proving the normal proof, direct proof. You see, right? I'm just going to assume this, then I arrive here. So to show that this is true by counter positive opposition. So let's check. We're given a statement now. They say, given that n is an integer, prove by contrapositive that if n squared is even, then n is even. So first what we do, before we think of anything, remember I told you that this will be P. N is an even integer, and then this will be Q. Q is an even integer. Remember here, we don't declare negated statements, we only declare positive statements. You say, right? So we have that n squared is an even number, which is P, and n is even integer, which is that. They're all even integers, right? Then when we assume, we are going to assume the negation of Q. If we're using contrapositive, we are going to assume, check here, Q says that n is an even integer. It means that when I suppose, I'm going to assume that n is odd. And then I'm going to write what is meant by n being odd. Please write it the same way which I told you to write, right? Like the previous examples. You are supposed to assume n is odd integer. After assuming that n is odd integer, we are going to do this. What do we mean when we say n is odd? It means that n is equal to 2k plus 1 for some k element of an integer. You say, right? And then from there you can say then you take this one now. Remember this here, it says that n squared is even. It means that you must arrive at the opposite. The negation of even will be odd. So you must arrive at n is odd. So when you plug it there, you're going to expand, you get this. And when you factor out the 2, you're going to have 2m plus 1, where m is equal to this, which is an element of an integer. Which then this leads us to have n squared being an odd integer. And then by contrapositive, we just copy this statement and say it is true. And then by contrapositive, we're going to say that if n squared is even, then n is even. You just copy this statement and paste after saying by contrapositive. Do we see that? So let's try a tutorial, one example there, or one exercise there, to see how can we answer such questions. So let's see. Okay, you see here, they say prove the following using contraposition. Right, so I'm gonna do this. I'm going to prove this using contraposition. So let's check. They say prove the following using contraposition. Then they give us A, right? A, they say that if m is odd integer, then m plus 1 is even. So let's check. We're going to prove this. Prove in A. I'm going to write proof first. Remember, this is how you prove. You write proof, then you assign your P, you assign your Q. Our P is this one. M is odd integer. So you're going to say M is odd, or is an odd integer. Then m plus 1 is even. You see, right? Then after writing this, we are going to assume since this is contrapositive, we are going to assume the negation of this. You see right there. Since this is contrapositive, you can just say assume negation of P and deduce not negation of P, assume negation of Q and deduce negation of P. So in other words, I'm going to suppose, or I'm going to just assume the opposite of this. I'm going to assume that m plus 1 is odd. I'm going to assume that m plus 1 is odd integer. What do we mean when we say m plus 1 is odd integer? We mean that m plus 1 is equal to 2k plus 1 for some k element of an integer. You see, right? And then now we need to arrive where m is even. We need to arrive where, remember, we need to deduce the negation of P, which means that m must be even. So we're going to have this. We have this from the beginning. M plus 1 is equal to 2k plus 1. And this implies that m is equal to 2k plus 1 minus 1. And here we're going to get 2k. M is equal to 2k. You see, right? Now, when we check this, we get that, or not even to say we get that, we can even just say, therefore, m is even integer. If m is even integer, we'll say by contrapositive, if m is odd integer, then m plus 1 is even integer. Here I'm just copying the original statement. You see the original statement is saying this. So after proving that and you get your answer, you're going to just copy and paste that statement, that question. You see, right? That's the conclusion they want. You just copy and paste. Now, let me do this. Let me leave you to do C. Can we try to do C? Let me leave you to do C. Let me stop this recording.